transition to silicon-dominant battery anodes is hitting a hard chemical supply wall. Global electronic-grade silane gas capacity is highly inelastic, growing at just 4.4% annually. This slow growth is constrained by high capital requirements and 3-year facility build cycles. Meanwhile, battery-grade demand is scaling exponentially due to gigafactory pipelines. By late 2025, total demand will cross global capacity, initiating a structural deficit. This deficit is projected to reach 41,000 metric tons by 2030. Anode architecture choices dictate chemical supply chain exposure. Silicon-carbon anodes using chemical vapor deposition requires 0.45 kilograms of silane per kilowatt-hour. Pure silicon nanoparticles require 1.35 kilograms. At $15 per kilogram of silane, these advanced anodes are economically viable. However, if silane prices spike to $100 per kilogram, pure silicon anode costs rise to $150 per kilowatt-hour. This 325% cost escalation completely erases the economic benefit of the 53.3% increase in volumetric energy density. This dynamic replicates the solar polysilicon crisis of 2004 to 2008. During that period, a sudden demand shock drove polysilicon prices from $32 to $385 per kilogram. Electronic-grade silane is on a matching trajectory, projected to rise from $12 to $110 per kilogram by 2027. Capital expenditure for new silane synthesis plants is high, costing $120 million per 10,000 metric tons of capacity. This capital barrier ensures that supply responses will lag demand by 3 to 4 years. Battery manufacturers face a guaranteed multi-year pricing squeeze. Advanced semiconductor manufacturing requires extreme chemical purity. Currently, North America and Europe face severe structural deficits in semi-grade 5 sulfuric acid. North America lacks 20,000 metric tons of annual purification capacity, while Europe faces a 13,000 metric ton shortfall. This geographic concentration in East Asia exposes Western fabs to severe supply chain vulnerabilities. This deficit cannot be resolved through standard transoceanic shipping. Semi-grade 5 acid is highly reactive and leaches metals from container walls over time. Standard fluoropolymer-lined tanks exceed the critical 100 parts per trillion impurity threshold after 27 days in transit. Only specialized, capital-intensive PFA-lined containers can preserve purity, but their global fleet is highly constrained. Supply bottleneck is compounding as advanced fabs scale up. Transitioning from legacy 28 nanometer nodes to leading-edge 3 nanometer nodes increases wet processing steps by over 300%. This drives a 448% surge in ultrapure acid consumption per wafer. The upcoming 2 nanometer node will push consumption to 58 liters per wafer, exacerbating the Western supply crisis. The global niobium supply chain exhibits an unprecedented level of geographic and corporate concentration. A single mine, the Araxá operation in Brazil, run by CBMM, controls 84% of global output. Combined with adjacent deposits, Brazil commands 93% of the global market. This creates a single point of failure without parallel in modern metallurgy. The only viable alternative of scale is the Niobium mine in Canada. However, Niobium contributes just 6% of global supply, leaving Western industrial bases highly exposed. Niobium extraordinary metallurgical leverage. Adding just 0.05% niobium by weight increases steel yield strength by over 30%. This microalloying process allows engineers to reduce structural steel mass by up to 25% in major infrastructure projects. Because alternative elements like vanadium require much higher concentrations, niobium is practically non-substitutable. This chemical efficiency locks global infrastructure and automotive manufacturing into a highly concentrated supply chain. The demand profile for niobium highlights its systemic importance. High-strength, low-alloy steel production consumes nearly 90% of global supply. However, the remaining 10% represents highly critical, inelastic defense and high-tech applications. This includes nickel-based superalloys for military jet engines and superconducting magnets for advanced medical imaging. A supply disruption at Araxá would immediately halt these critical supply chains. No strategic stockpiles can offset a prolonged shutdown of the primary Brazilian deposit. The Danish Straits impose an immutable physical bottleneck on Baltic maritime logistics. The Great Belt Route T features a strict draft limit of 15.0 meters. This ceiling completely excludes Capesize and post-Panamax vessels from direct egress. Exporters must rely on smaller, less efficient hulls. A fully laden Panamax vessel operates with a marginal safety clearance of just 0.5 meters. This physical constraint forces a reliance on Handymax and Supramax vessels, tripling the required transits for equivalent cargo volumes and compounding regional port congestion. Regulatory and geopolitical pressures are actively reshaping Baltic trade flows. Dry bulk transits fell 13.4% between 2021 and 2023. Fertilizer volumes, specifically potash and ammonium nitrate, contracted by over 32%. Conversely, liquid energy flows remain highly inelastic. Crude oil transits averaged 3.2 million barrels per day through 2023. This volume is sustained by shadow fleet operations designed to bypass Western sanctions and maritime oversight. Denmark is utilizing regulatory and environmental enforcement as an active economic lever. Average transit delays through the Straits surged by over 400% in 2023. At the same time, mandatory pilotage and compliance fees more than doubled. This operational friction acts as a targeted tariff on Russian exports. The combined delays and fees add up to $1.20 of additional cost per barrel of crude. This structural tax erases margins for Baltic exporters and forces a reallocation of global shipping assets. Hypersonic flight requires structural materials that survive extreme atmospheric friction. Carbon-carbon composites are the industry standard, but their manufacturing is constrained by physics. Achieving a density of 1.90 grams per cubic centimeter requires 5 chemical vapor infiltration cycles. This process demands over 20 weeks of continuous vacuum furnace dwell time. The kinetics of densification exhibit steep diminishing returns. The first cycle adds 0.27 grams per cubic centimeter in 3.5 weeks. By contrast, the sixth cycle requires 5.5 weeks to add a marginal 0.04 grams. This kinetic bottleneck prevents rapid scaling through simple capital injection. Military procurement schedules for hypersonic weapons are fundamentally decoupled from industrial reality. By 2026, global defense demand for carbon-carbon composites will reach 715 metric tons per annum. This exceeds total global manufacturing capacity by over 32%. The resulting structural deficit will stall missile and glide vehicle production. The defense industrial base is highly consolidated and vulnerable. Over 85% of Western production is concentrated within just 5 defense contractors. United States defense demand alone is projected to scale over 300% by 2030. This extreme concentration leaves no margin for operational disruptions. No viable substitute materials exist to survive sustained hypersonic flight. Carbon-carbon composites exhibit an anomalous property where tensile strength actually increases at high temperatures. Strength rises by 5% up to 1,600 degrees Celsius. This behavior is unique among structural materials. Alternative materials fail rapidly under these thermal loads. Conventional nickel-based superalloys lose all structural integrity below 1,400 degrees. Ultra-high-temperature ceramics retain strength but are highly brittle and heavy. For nose cones and leading edges, carbon-carbon remains a non-substitutable material. Ammonia is the primary chemical carrier for transoceanic hydrogen transport. However, converting ammonia back into hydrogen gas imposes a severe thermodynamic penalty. Cracking is highly endothermic, requiring significant thermal energy inputs. Ruthenium-catalyzed systems operating at 550 degrees Celsius achieve a net hydrogen yield of 65%. This process requires 4.8 megajoules of thermal energy per kilogram of ammonia. This thermal energy is typically generated by burning a portion of the imported ammonia itself. Nickel-based catalysts operate at 800 degrees Celsius. This higher temperature increases the thermal energy penalty to nearly 35%. To meet Rotterdam's 2030 import targets, the port will require up to 9.6 gigawatts of continuous thermal energy just to drive this reaction. Port of Rotterdam faces a massive physical infrastructure gap. The 2030 target of 20 million metric tons of ammonia imports requires 15 gigawatts of thermal cracking capacity. Current planned projects total only 9.2 gigawatts. This leaves a structural capacity deficit of nearly 39%. To avoid stranded import terminals, operational cracking capacity must grow at a compound annual rate of 90.2%. Under current construction timelines, high-purity hydrogen output will reach only 1.62 million metric tons per year. This falls far short of the 2.64 million metric tons implied by the import target. This bottleneck mirrors the early liquefied natural gas infrastructure delays of the 1970s. Micro-level chemical engineering constraints dictate these macro-level economics. Project developers face a stark trade-off between catalyst cost and operating temperature. Ruthenium-based catalysts operate at lower temperatures but cost $8,400 per kilogram. Nickel-based alternatives are 300 times cheaper but require temperatures above 750 degrees. These extreme temperatures accelerate thermal degradation and reduce catalyst lifetime to 3,000 hours. Furthermore, ruthenium is highly sensitive to impurities like water or oxygen. Removing these trace contaminants requires extensive upstream purification. This step adds up to $0.25 per kilogram to the levelized cost of the delivered hydrogen. The scaling of long-duration energy storage is constrained by a highly inelastic chemical supply chain. Over 70% of global vanadium is recovered as a secondary byproduct of steel slag processing. China and Russia combined control 81.8% of this supply. Primary mining remains highly localized, leaving the market structurally dependent on global steel production cycles. Utility-scale flow batteries require massive volumes of high-purity vanadium pentoxide. A standard 100 megawatt, 800 megawatt-hour project consumes 6,400 metric tons of electrolyte. By 2028, high-growth battery demand combined with traditional steel metallurgy will exceed global refining capacity by over 50%. This physical bottleneck threatens to stall the deployment of long-duration grid storage. Vanadium market dynamics expose battery developers to severe external price shocks. The 2018 price spike to $16.40 per pound was driven entirely by Chinese rebar regulations. Because electrolyte accounts for up to 45% of system capital expenditure, these spikes alter project economics rapidly. A price swing to $15 per pound increases the levelized cost of storage by over 40%, rendering projects unbankable. Solid-state thermal management relies on tellurium, one of the rarest stable elements in the Earth's crust. Its crustal abundance is limited to just 1 to 5 parts per billion. Because primary mining is economically unviable, over 90% of global supply is recovered as a byproduct of copper refining. This creates a highly inelastic supply ceiling. Global tellurium output reached just 670 metric tons in 2024. This volume is structurally capped by 27.8 million tons of refined copper production. The recovery yield remains locked below 25 kilograms per 1,000 tons of copper, preventing any rapid supply response to external demand shocks. Downstream manufacturing exhibits extreme geographical concentration. China controls 62% of raw tellurium refining, which scales to an 85% monopoly in finished thermoelectric module assembly. Western domestic capacity across the entire value chain remains below 8%. This concentration is enforced by material science constraints. Synthesizing high-purity single-crystal bismuth telluride requires precise Bridgman-Stockbarger crystal growth techniques. Because these crystals are highly fragile, transoceanic transport introduces severe microfracture and contamination risks. Consequently, finished module assembly must remain co-located with East Asian crystal growth facilities. This rigid supply chain is colliding with an unprecedented demand shock from high-performance computing. Thermoelectric coolers are critical for stabilizing high-density optical transceivers, including 800G and 1.6T architectures. Demand in this sector is projected to scale from 2.1 million units in 2020 to 54.2 million units by 2026. This rapid expansion is outpacing the baseline telecom growth of 13.5%. Because tellurium supply is tied to copper smelting, it cannot scale to match this trajectory. This divergence threatens a structural deficit reminiscent of the helium-3 crisis, leaving Western hardware manufacturers highly vulnerable to sudden export restrictions.